Greetings and welcome back. Today we'll be looking at the two different types of nucleophilic substitution reactions, both Sn2 and Sn1. Sn2 is one that we've done in the past, but Sn1 is kind of a variation of Sn2. It is less useful in lab, creates problems, but it's one that you need to be aware of how it works and why it works and when it works. In general, any substitution reaction begins with a carbon with a leaving group attached, usually a halogen, but not always. We add in a nucleophile, and what will happen is the nucleophile will kick off the leaving group and replace it with a new bond to the nucleophile. So, in effect, what we've done is substituted a leaving group for a nucleophile. There's two ways that this reaction can happen. The first one, as I mentioned, we've already covered, but we will recap it here quickly. An Sn2 reaction requires a strong nucleophile, so a nucleophile with a minus charge, and we are going to have a carbon attached to a leaving group. What will happen in this reaction, the mechanism, is that the nucleophile attacks the carbon, kicks off the leaving group all at once, and then we will end up with that new bond to the nucleophile. And then the leaving group leaves and it has a minus charge. Energetically, this is a very favorable reaction because of the fact that you have gone from a nucleophile, which is negatively charged, to a halogen with a negative charge. And therefore, it's a one-step reaction, it's second order, and it goes very fast. So I'm going to write that down. One step, second order. The reason for second order is that the rate depends on the concentration of both of those reactants. So it depends on the concentration of that strong nucleophile and on the concentration of the alkyl halide, whatever that is. Because those guys would have exponents of 1, 1 plus 1 is 2, and that's the second order reaction. I'm going to give you a very brief introduction to Sn1 here, and then we'll talk about it more in depth in a few slides. So with Sn1, what happens is you start off with the leaving group. But if you have a weak nucleophile, that is to say a nucleophile that's not negatively charged, the nucleophile isn't going to want to come in and share its electrons. A strong nucleophile going backwards is one that is more stable after it's made the bond. Therefore, it's unstable with a minus charge, and it really wants to react. In the case of Sn1, the nucleophile doesn't really want to share the electrons unless it needs to. So it just sits there. In the first step of an Sn1 reaction, the leaving group leaves all by itself. That will result in the formation of a carbocation. A carbocation is an extremely strong electrophile, and therefore the nucleophile in a second step can form a bond, and that will result in the new bond between the nucleophile and the carbon that had the leaving group attached. So, in this case, the slow step is the first step, and we can draw out our energy diagram for this reaction. We would start somewhere that we would say is kind of a medium energy, and that first step would be very slow because you're actually going to a less stable situation. You're going from a neutral situation where the halogen would rather be by itself, it would rather be minus charged, and that's the hallmark of any good leaving group. It would rather take its electrons and leave. But in the first step, the only thing that happens is this bond breaks. The C plus is really unstable, so this is a higher energy intermediate. And then in the second step, which goes down to product, you would get down to a lower energy product. So overall, the Sn1 and the Sn2 reaction do the same thing, but there are some differences. For the Sn1, it's a two-step reaction, and the first step is rate limiting. So the rate is going to be just equal to the rate law for the first step, which is little k times just the concentration of the alkyl halide. You'll notice that the nucleophile doesn't do anything in the first step. It just sits there as a spectator ion. The nucleophile isn't involved until the second step, which is the fast step. Because the rate of an overall reaction depends on the rate of the rate-limiting step, or the slowest step, this first step is the only one that matters. And the only reactant in this first step is our alkyl halide. Because this completely depends on the concentration of one reactant, therefore, this is a first-order reaction. The only way that we know this for sure is that we test the rate. We tinker around with the concentrations. You remember from general chemistry too, we can solve for the rate law by rerunning the reaction at multiple different concentrations. Well, we found experimentally that by changing the concentration of a nucleophile, an Sn2 reaction can go faster or slower. But changing the concentration of the nucleophile in Sn1 has no effect whatsoever on the rate. The only concentration that you can change that affects the rate is the concentration of the alkyl halide. Therefore, experimentally, we determined that this was a first-order reaction, which led us to understanding of the mechanism. Big picture, Sn2 is a great reaction. It happens all in one step, and you only get one product. I mean, you get the halogen falling off, but you only get one real product up here that we care about. But in the case of Sn1, you generate a carbocation intermediate, and the carbocation intermediate can do something funky, and that is called rearrangement. We will talk about that. That guy can rearrange. Essentially, it's so unstable that it will do anything it can to become neutral. Well, if it rearranges, you might have multiple different carbocations, and the nucleophile can attack in multiple different ways, and therefore, oftentimes, we will end up with multiple products. And since the goal of organic chemistry, at least synthetic organic chemistry, is to make a product, if you end up with multiple products, it is not that great of a thing. You have to go through and separate them all out. Your yield will be much lower. And therefore, generally, Sn2 is considered superior for what we're trying to do in lab. However, once again, Sn1 is something we need to be aware of. All right, so let's look more deeply at Sn2, and then we'll go into all of the details of Sn1. So for Sn2, it requires a strong nucleophile. And it also requires an accessible electrophile. So let's look at some examples of this. With Sn1, if we have like a chlorine right here, and we add in something like sodium hydroxide, or an OH minus, what will happen is, as we've laid out already in class, that chlorine is a good leaving group. Therefore, this carbon right here, the carbon attached to it, is a good electrophile. And OH minus is a strong nucleophile. So the nucleophile can attack the electrophile, kick off the leaving group, and we would get a new product that has broken the bond between carbon and chlorine and made a new bond between that same carbon and oxygen. And that would be our product. One thing that I have mentioned before, but it's worth kind of remembering, is that this is a backside attack. The OH will always attack from the opposite side of the chlorine, and therefore you would end up inverting that carbon. You always get one product, even whether it's chiral or not. Your OH minus or your nucleophile will attack from the opposite face of the leaving group. So one thing to consider is that you will always swap around your stereochemistry. This does matter whenever you have a chiral starting material. So for instance, if we had a CH3 right here, that CH3 would now be in a different location. So you'll notice that if we track out the chirality, this carbon, or this chlorine is 1, this big old carbon group is 2, the CH3 is 3, so this would be R, since H is in the back. Well, in this case, oxygen is 1, this big old group is 2, and this CH3 is 3, H is in the back again, so this would be S. So it's going to swap your stereochemistry if you have a chiral starting material. All right, so the second thing to consider is that it requires an accessible electrophile. And by that we mean that it needs to have a primary alkyl halide, or that's much better than a secondary alkyl halide. And a tertiary alkyl halide just won't work. So what I have drawn now, our amended version of this, is a secondary alkyl halide because I have this carbon right here, the one attached to the chlorine, has 2 carbons attached. Therefore, it is secondary. Well, the more carbons you add onto that position, so in this case, let's put a CH3 here and a CH3 there. Well, so much of what we've talked about in this class is about sterics. So we said that if you had an O- attached to a lot of carbons, it couldn't reach in there and attack the backside of that sp3 orbital, and therefore you wouldn't be able to get any reaction. So this goes two ways. You can't have a nucleophile that's too bulky, or else it won't be a strong nucleophile anymore. Remember when we talked about differentiation between nucleophiles and bases, that was the big thing. In order to be a strong nucleophile, you can't have too much bulk. Well, for the sake of Sn2, if you have too much bulk all around the electrophile, it won't work either. So it turns out that this reaction won't even occur. We would get no reaction, and therefore the final products would just be the same thing you started with because nothing will happen. The reason for this is that there's too much bulk around the electrophile. So if you have a tertiary carbon that is your alkyl halide, so once again we're talking about this carbon right here, that's the electrophile. If it's attached to 3 carbons in the leaving group, it's too bulky, our nucleophile can't even get in there, and it's just not going to work. So you need to have a primary electrophile or a secondary electrophile for Sn2 to work. All right, so that's it for Sn2. Remember, a strong nucleophile needs to be negatively charged. We can't have too much bulk around our electrophile, and in terms of stereochemistry, we're always going to invert our chiral carbon if we have one as our electrophile. Sn1, on the other hand, remember going back a couple slides, it doesn't have a strong nucleophile. So this happens with a weak nucleophile, or, I guess I should say or a crowded electrophile. And that is to say, your tertiary CX is better than your secondary CX. And then for primary, it doesn't really work. And the reason for this has to do with the actual nature of the molecule. So I'm going to draw out that exact same molecule that didn't work for Sn2 because there was too much bulk around it. This guy right here. So in Sn1, I'm not going to add in hydroxide. I'm going to add in, let's go with water. So water is an example of a molecule that is a weak nucleophile because it's neutrally charged. It has electrons that it can possibly share to make a new bond, but it doesn't really want to. Right here we see that that chlorine is still a leaving group, and that this carbon attached to it would be our electrophile. Well, what we said is that the strong nucleophile would reach in there and try to attack, but a weak nucleophile doesn't want to reach in there and attack. It just kind of is happy to sit around and wait. So in the first step, the leaving group would just leave. That would create a carbocation that looks like this. Now notice that I've gone from wedges and dashes to writing everything nice and flat. The reason for that is that a carbocation, or a C+ with 3 bonds, is sp2, and therefore it has essentially an empty p orbital sticking towards you and backwards the way that it's drawn right now, and it has no chirality. So the nucleophile in the second step, which was just kind of waiting around, it didn't want to attack, but now the electrophile is so incredibly strong that our OH2, or our weak nucleophile, will share its electrons, just because it has to, not because it wants to. Well, it could share the electrons from the front or the back, so we actually have no stereochemistry when it comes to Sn1 reactions. We lose our chirality in the middle. So if that guy attacks from the front, we would have something like this. It would be an OH2 with a plus charge. And then we would have a methyl group there and a methyl group right here. It could also attack from the back. And in this case, the carbon isn't chiral, so these will both be the same molecule, but it can matter if that carbon was chiral. So we would get basically 2 different products at that point, because that water could come in from the front or the back. A p orbital has 2 lobes, one, in this case, right here, sticking out at you, and one going backwards. So the water could come in from the front, which would make this guy, or it could come in from the back and make this guy. All right, and we're still not actually done. We have attached the nucleophile, but in the case of weak nucleophiles are almost always neutral. And so when they attack, they would become positively charged. Well, the reactivity of an O+ is that it is a really good leaving group. And so the result of this is that the carbons next door are electrophiles and the hydrogens next door are acidic. So the easier reaction to do between nucleophile-electrophile and acid-base is acid-base. It has a much smaller activation energy. It goes really fast. It's really easy to break a bond to hydrogen. So because those guys are strong acids, what they need to react with is a weak base. It just so happens that we still have water sitting around, and water is a weak base. So water can pull that hydrogen off. It would bring the electrons back to that leaving group, and we would get our final product, which could look like this. We had an additional water that pulled off a hydrogen, so we would technically get a little bit of H3O+, and all that would matter in that case is that the water in which you're running this reaction would become a little bit more acidic. All right, the same thing can happen over here to this product. This is, of course, the same product, but I will draw it again. We have some water sitting around because in order to do this reaction, we need to have a lot of water. So usually we just use water as our solvent. In other words, we would take this guy and mix it with water and heat it up. So let's look at the reactivity here. An O+ is a good leaving group. Therefore, the hydrogens next door are acids, and the carbons next door, which would just be this one, are electrophiles. We don't have a good nucleophile. We have a weak nucleophile. But we do have really strong acids, and so water can be a weak base. Grab one of those hydrogens. The leaving group basically leaves the hydrogen. It unshares electrons from that hydrogen, and we would get a final product here that would be neutral. And instead of being an OH2+, it would just have that one hydrogen left over and be an OH. All right, this last step here is often called deprotonation, and it happens whenever you have an O+ or an N+ that you just need to pull a hydrogen off of. It's a very simple thing to do. You don't need to add any reagents except for water. But it's something to keep track of because think of it more like bookkeeping. At the end of the day, if you have a little bit too many hydrogens, you just need to pull one off. It doesn't really fundamentally change the identity of this product. They are slightly different, but really we're just pulling a hydrogen off of a spot that had too many hydrogens. That's an easy thing to do. It's a very simple mechanism. It's just the acid-base mechanism. And the driving force for this is that an O+ attached to a hydrogen is a very strong acid. So you don't need a strong base, you just need water. So we will do deprotonation a lot. It's a very simple thing, but it's one to keep in mind if you ever make a product that has a positive charge. For instance, an O+ or an N+. All right, so this is how Sn1 reactions happen. Note that the difference is we need a weak nucleophile, that is to say water. It can technically work with a strong nucleophile, but usually we wouldn't get Sn1 in that case. And a crowded electrophile is also something that works very well for Sn1. So see if you can tell me why. All right, so the reason why is that the first step is that the leaving group leaves. When the leaving group leaves, you generate a carbocation. Carbocation is a C+. A C+ does not have enough electrons. Therefore, for a carbon that doesn't have enough electrons, the stablest carbocations would be those that have a whole lot of carbons around them. So, Sn1 and Sn2 work great together. Sn2 is really good when you don't have a lot of carbons nearby because you just attack all at once and kick off the leaving group. Too many carbons would make it too bulky, which wouldn't make it work. In the case of Sn1, you don't attack and kick the leaving group off all at once. Instead, you wait for the leaving group to fall off. But when the leaving group falls off, you create a carbocation. There is no carbocation with Sn2. Everything happens at once. But in Sn1, you have a carbocation intermediate. And the more carbons there are around it, the more stable it is. All right, so this is how Sn1 works. we're going to add the twist of rearrangement, which I mentioned in pink on the slide before this, and that will be the end. So here we go. All right, so let's look at what we have for this reaction. Well, we have a leaving group right here, the bromine. It's attached to a carbon that has two carbons attached. So this is a secondary CX. All right, secondary CXs, those are okay for Sn2 and they're okay for Sn1. But when we look at our only possible nucleophile, it is neutral. So therefore this guy is definitely a weak nucleophile. And in that case, when you have a weak nucleophile, you cannot possibly have Sn2. So this is going to go by the Sn1 mechanism. So the first step of an Sn1 mechanism is that the nucleophile isn't strong enough to just come in and kick the leaving group off. So it just has to wait around for the leaving group to leave. And when that occurs, you would get this carbocation. But one thing we've seen experimentally is that you end up with multiple products with Sn1 reactions sometimes. And let's draw this guy out as a Lewis dot structure so that we can see why. All right, this is going to, again, be the exact same molecule, but I want to be able to see my hydrogens. In reactions in which things can possibly happen nearby, we should draw in all of our hydrogens just so that we have evidence of what could possibly occur. All right, so what we see is that this is a secondary carbocation. Secondary carbocations are okay, but they're not very stable. They could be more stable. So what's more stable than a secondary carbocation? Well, it's a tertiary carbocation. Because again, the fundamental problem with the C+ is it's a carbon that doesn't have enough electrons. So oftentimes, what will happen simultaneous to the leaving group leaving is that a neighboring hydrogen with its electrons can move over. This would be resharing. So I am going to circle the electrons that move. It's not just the hydrogen that moves, but the hydrogen and its electrons can move over one spot while the leaving group leaves. This is called a hydride shift. Hydride, which is H-, kind of like chloride or bromide. It's a hydrogen with a minus charge, which means an H with a pair of electrons. A hydride can shift over one carbon, but the only reason that that will happen is if it can make the carbocation more stable. So, if that occurs, what we would see is that this hydrogen would move over a spot. That carbon already had a hydrogen, so now the carbocation is right here. An easier way to see this is in the Lewis dot structure. Essentially, that guy just hops over one spot. This only happens, big asterisks, asteri, only happens to a carbocation. And it's always a possibility for this to happen to a carbocation. And it only occurs if the carbocation can become more stable. So, in the case of the leaving group leaving all by itself, we got a secondary carbocation. But in the case of the leaving group leaving and the hydride shift occurring, we get a tertiary carbocation. So what's going to happen in this reaction is you will actually get both of those things, because it's easier to just have the leaving group leave without anything else occurring, which would give you this secondary carbocation. It's harder to have the leaving group leave with a hydride shift, but it gives you a more stable intermediate. So what will happen is, this is like the lazy guy that's not so good, and this one is a little bit more committed to making a more stable carbocation, but it takes a little bit more work. You get both of these. So the second step of Sn1, which is when the nucleophile shares its electrons with the carbocation, will happen to both of these, and so you'll end up with multiple different products. So let's walk through those. In this case, I'm going to do it from my hydride shifted version. And so the methanol in this case, there's the lone pairs that can be shared. That would give me our OHCH3 with a plus charge. If you have an O+, it's a good leaving group. Therefore, the hydrogens next door are strong acids. So we will have our methanol share electrons with that hydrogen, deprotonating the hydrogen, and giving me a final product that looks like this. And that would be an ether. All right, the other way for this to occur would be for your methanol to attack the non-rearranged version, which is the less stable intermediate. So the oxygen, once again, is the only thing that can possibly be a nucleophile, and the carbocation is definitely an incredibly strong electrophile. So we would make this compound right here, which is charged. And in that deprotonation step, we can use some more methanol to simply pull off that extra hydrogen, which would give us a neutrally charged ether. These two ethers are not exactly the same. This would be product number 1, and this would be product number 2. Furthermore, like we mentioned on that last slide, this oxygen could attack from the front or it could attack from the back. So realistically, you would get this guy and you would get this guy. This carbon right here is achiral, so you wouldn't get 2 different products over here. So we would actually get 3 different products of this reaction. So Sn1 is the worst. There's a lot to consider for you as a student learning how it works. There's also a lot to consider in terms of the reaction. We have a lot of things happening. We do not want a lot of things to happen. So if we can, we try to avoid Sn1 at all costs. Whew. All right, so that's a lot. Let me give you one more example, and I'd like you to try to work out on your paper, this will take time, the products of this reaction. All right, thank you very much. Please bring any questions you have to class, and I will see you soon.